Hello, everyone. My name is Satyam, and along with my colleague Kshitij, we are going to share some of our experience building a graph compiler for the D-Matrix AI accelerator. Before we start, it's important to understand why. Why do this? Why even build an accelerator? And some of you may have heard the term memory wall, or the AI barrier, or compute starvation. They're all the same thing, and essentially mean that the traditional architectures with their fastest HBM memory cannot satisfy the demands of modern-day AI computing. So we set out to build something which is fundamentally different and which can give us 10 times, 20 times faster memory performance needed for these. That takes us to the Corsair accelerator. So Corsair architecture is built using data flow and modular building blocks, which can be composed into larger systems. We use in-memory computing technology for fast as well as energy-efficient matrix multiplications and augment that using copious amounts of fast and distributed SRAMs on chip that are used for storing the tensor parameters. One thing to note for later in the talk is that each chiplet is divided into 4 quadrants or quads, and each quad is a software targetable independent unit of programming. Another couple of things to keep in mind. One is that we have a pretty sophisticated memory hierarchy, including multiple tiers, but it is not based on caches. All of our memory is transparently visible to software, and the onus is on the programmer and the compiler to carefully orchestrate both the placement as well as the movement of data on these memories. The second thing is, very likely, when we have a model of a substantial capacity, it's going to require us to distribute that over multiple devices, and doing so in an adequate parallelism strategy. Now, the question is, how do we even start thinking about program representation for this weird in-memory computing architecture with fancy memory hierarchy in a way that also scales to multiple devices? Thankfully, we have abstracted all of that complexity pretty much into a compact instruction set. So the Corsair ISA comprises of a handful of instructions comprising data movement, load store, vector and matrix computation, program control, as well as data reshaping. And on the right-hand side, you have a toy example of what a simple matmul is going to look like using these instructions. And we will talk more about that in the later parts. With that backdrop, when we start building out the graph compiler as part of the larger software stack, we will end up with a handful of challenges, obviously. To this community, it's not a new thing that building a compiler is hard. Some of these challenges are unique to us. Some of them are universally applicable. And in general, they fall into these 3 categories. How easy or difficult it is to capture a large variety of algorithms through the compiler. And in case of machine learning, that would translate to what kind of ML architectures can be compiled. The second is, what kind of control and power do we provide to the developers or the kernel authors to be able to express their optimization hints as well as any programmatic constructs and faithfully represented downstream? And the third is using all of that, not only the compiler techniques, but the programmer intents. How well can we harness the true benefits of the architecture and get the performance that it promises? So our approach to solving some of these challenges, as well as more, is to take a hybrid route. And by hybrid, it means we have a compiler stack, we'll talk about that, which is based on MLIR, and that is complemented by a rich library of high performance as well as user-optimized kernels. These kernels can come into an external dialect like a triton, which we can support functionally, but there are structural differences between what triton expects and the kind of abstractions our DSLs need. So we have other approaches to writing kernels at a slightly better abstraction down below. And in each of these cases, the kernels get translated into an IR or a dialect of MLIR that gets ingested into the compiler for subsequent processing and optimization. Now, to take a look at what happens inside of those core pieces of the compiler, I'll hand it over to my colleague.
Thank you, Satyam. So I'm going to start with a broad strokes view of our hybrid compilation pipeline, and then I'm going to dive deeper into some of the interesting components across our front end, middle end, and back end. So we start with PyTorch models that we lower via Torch MLIR into our compiler front end. In the front end, we perform SPMD-based partitioning, padding, tiling, quantization into our numerics, and constant folding. The output of this phase is a bunch of affine loops that are operating over tensors. Then comes the middle end. In the middle end, this is where Triton integrates into our compiler as a bunch of affine loops. In the middle end, we perform producer-consumer style fusion, bufferization, as well as vectorization, where we lower ops operating on tiles of data into ops operating over 64 by 64 virtual vector registers. Output of this loop is a bunch of parallel loop nests communicating with each other via the DDR memory. Then comes the compiler backend. This is where our custom DSL, lowered into DLIR, integrates into the compiler. In the backend, we perform SRAM and register allocation, instruction selection, instruction scheduling, kernel stitching, and lowering to a thread model. Output of this phase is the DMX ISA, the assembly for our hardware. So I mentioned one of the transformations that we do is SPMD partitioning. Let me dive deeper a little bit into that. We perform SPMD partitioning in stable HLO, as a result of which we get quad-level symmetric compute graphs. The rest of the compilation pipeline thereafter operates on these quad-level symmetric compute graphs. SPMD partitioning isn't the only way for mapping a compute graph over a compute mesh. For us, however, it makes quite a lot of sense. One of the most important models for us to support is attention-based models. And SPMD partitioning allows us to naturally tie the independence and the symmetry present across the different attention heads of a multi-headed attention model to quads, which are the autonomous units of execution in our hardware. Let's now walk over concrete examples to understand what a 512 by 512 MACML looks like as it's progressively lowered through our compiler stack. This will help illustrate the rich abstractions afforded by MLIR that enable us to faithfully model our hardware and thereby optimize for it. So super early in the pipeline, we have the high-level algebraic op corresponding to a single MACML. This single MACML op is then broken into 64 MACMLs, each 64 by 512 by 64 in size. We choose to tile by those dimensions because that's the biggest MACML our MACML engine can handle at once. Another thing to note here is that we've also lowered from FP32 numerics to Corsair BFP numerics. So I mentioned that our MACML engine can handle a 64 by 512 by 64 MACML at once, but in the hardware, this actually happens as 8 different 64 by 64 MACMLs. And there's 16 different vector registers involved, 8 for activations and 8 for waits. So in this slide, you can see that we take a progressive lowering step towards this kind of representation. We then finally vectorize the MACML and make the 16 different vector registers that are involved in the computation explicit in the IR. Also explicit in the IR is the partial product reduction that happens across these 8 different MACMLs that ties them together as part of a single MACML. Finally, we lower to a thread-based model, as part of which we convert each affine parallel loop nest into a GPU call running on up to 8 cores inside a gang. We model each of the cores as threads. One thing to note here is that although we're modeling cores as threads, our hardware doesn't actually require us to do so, and our cores can actually run divergent workloads. Throughout the lowering, we use a number of affine dialect-based optimizations that have been mentioned here. I'm going to avoid talking about them in detail in the interest of time. Regardless of whichever path code takes through our compiler, whether it's PyTorch, Triton, or custom DSL, they all converge to DLIR, our custom dialect that has feature parity with our hardware ISA. DLIR models our hardware's ordered queue execution primitives, and a DLIR graph represents a fully scheduled workload on our hardware. DLIR is our egress out of MLIR, and it lowers to our hardware ISA pretty mechanically. So to wrap things up, MLIR has enabled us to address some key challenges of delivering a ML compiler toolchain. It's allowed us to meet our customers where they are today, and its flexible and rich dialect system has allowed us to faithfully model our hardware and thereby optimize for it. It's also allowed us to build a single compiler that can support both code-gen and kernel-based approaches natively. As for our next steps, we'll be focusing on increasing our op coverage, improving our performance, and building up our kernel libraries. With that, thank you, and have a great rest of your evening.